Section 1.2, we have two learning objectives. One is we want to develop a taste for econometrics, that is by asking a question and then see how we can answer that question using economic data. And the second learning objective is that we are going to introduce certain basic statistical concepts that are used in econometrics. And these statistical concepts are also the background that is necessary for econometrics. So here is the question: do women live longer than men in Europe? And to answer these questions, we have data from the European countries, 15 European countries, and the data is collected for the year 2002. The data tells us about the average life expectancy of women in European countries and the average life expectancy of men in the European countries. These countries are Austria, Belgium, Denmark, Finland, France, Germany, Greece, Ireland, Italy, Luxembourg, Netherlands, Portugal, Spain, Sweden, and UK. Now, if you look at the data, you can simply answer that yes, definitely women live longer than men in the European countries, because if you compare it in Austria, the average life expectancy of women is 81.2 as compared to 75.4 as compared to 75.4 the average life expectancy of men. So they live around about 5 years longer than men in Austria. The same is true for Belgium, 81.4 as compared to 75.1. Again for Denmark, 79.2 as compared to 74.5. So it is evident, but it is by observation and we haven't applied any technique. Now, econometrics not only supports theory, but it also gives us the magnitude. For example, we now know that women live longer than men, but using econometrics, using statistics, we can also find out the magnitude. How much is this difference? And we can see that this difference is round about 5 years, but we can also justify that through the techniques, through the statistical techniques. And for that purpose, what we do, to answer the question, do women live longer than men in Europe? What we do is sum up all these life expectancy values for women and divide that by the number of observations. And these are the number of observations. We have 15 countries or 15 observations. This is the method for finding out the arithmetic mean, the formula. It is calculated through this formula, summation YW divided by N, and N is equal to 15. Let me rewrite that in, this is arithmetic mean, that is equal to summation Y by N. So we can find the average for men as well as women. Here it is 81 for women and 75.1 for men. Then we also find the standard deviation. Standard deviation is different from mean. Mean tries to find out the central value towards which the rest of the data try to converge, whereas the standard deviation tells us about the spread, how much the data go far away from the mean value. If it goes much farther from the mean value, the standard deviation value will be higher. But if the standard deviation value is low, it means that most of the data is somewhere near the central tendency value, that is the arithmetic mean. So to find out the standard deviation, the formula is summation Y minus Y bar and divide by N. that gives you the standard deviation for let me write the formula. Standard deviation, it is already written there, but for some people it is easy to see it this way. Summation y minus y bar, and we take the summation of that, then divide by the number of observations. I don't know why the author missed writing divide by n. I think it should be there. And then taking the under root of the whole value, right? So the standard deviation for women is 1.38 and for men it is 1.23. Then the next important value that we need here for our inference is the t-statistics. Now t-statistics is about the distribution of the data, and a normal distribution data have a shape like a bell shaped, and what actually it means is that most of the value are near the average. In this case we have y bar, so most of the value will be near 81, and there will be some extreme cases. For example, 83 will lie somewhere here. That is the maximum value in this data. Let me point it out. 83 will lie somewhere here, and the minimum is 79 point okay, here we have 79.2, this is 78.5. I think this is the least value here, so it may lie somewhere. So most of the data that will be near to 81, like 81.2, 81.4, 81.5, you can see that 81.3 and 82.1, they are near to the mean value, and there will be very few values like 79.2, 79.4, 79.7. they are lying somewhere here. There is only one value in the range of 78 and only one value in the range of 83, right? So most of the value will lie on the mean and fewer values in its extreme. This is the basic idea of a normal distribution. In order to calculate the t-statistics, and t-statistic having this normal distribution shape, the formula for that is that we are subtracting the two means from each other, that is 81 minus 75.1, so that we can see that these two are statistically different from each other, and we subtract that over here and divide it by somehow the average standard deviation of these two values, and that is standard deviation of women square, standard deviation of men square, that gives us variances, then divide by 15, that is the number of observation, and then taking the under root to counter the square that we have taken. So this gives us the t-statistics, and the technique here is, I'm not going into that detail here. Basically this is the method for hypothesis testing, but just to give you the taste, when we calculate this t-statistics, that is equal to 12.27, we compare that with the value of t-table, and the t-table at 5% critical value is usually 1.96. The rule of thumb is that we usually compare it with 2. So if t calculated is greater than the t table value, that is 12.27 is greater than 1.96, this means that there is less than a 5% chance of finding a t statistic of 12.27. 0.27 purely by chance when the true difference is 0. Here it means that in this case, in our example, it means that there is less than 5% chance that this difference is statistically 0, right? So it means typically, it in this sense means that 81 is quite different from 75. There is a statistical difference between the two values, and in common words, in layman's word, it means that women live longer than men. So we have answered here the first question: do women live longer than men in Europe? Yes, women live longer than men in Europe. But now we may have certain other questions, and using the same data concept, can we apply these results, the results that we have obtained here, to the rest of the world? To answer these questions, we need to know that whether this data represents the entire world or not. So chosen, it is not chosen on the basis of random sampling, but these are targeted European countries. The way they have been sampled, it tells us that we cannot apply this data to the rest of the world. This is related to the sampling technique, and I will come to that in the next slide, that what kind of sampling technique do we use in econometrics. But for the time being, you should know that since this is not a random sampling, this technique is this result is not applicable to the rest of the world. Then the second question: can the results of a single year of 2002 be applied to all other years? Now, this is a normal year. Nothing serious has happened in 2002 that could change the overall behavior. And 2002 can be a random year. So we can apply the results of 2002 to all other years in Europe, not outside Europe, but within Europe. These results may represent other years as well, but not some special years. For example, COVID-19. Now these results may have changed in COVID-19 because maybe COVID-19 attacks women more than men, and maybe the immune system of women is not as efficient as men to COVID-19. This is just giving a logic for it not to be true. Otherwise, the reverse can also happen, that men are more prone to COVID-19 as compared to women. But just I am informing you here that in 2002, the situation was normal. In any other subsequent years, if it is a normal year, then we can apply these results. But if it is not a normal year, these results may vary. Now the final question here: are these methods adopted here technically sound? Can we rely on the mean and standard deviation? And are they the best measure? So in order to answer this question, let me move on to the next slide and see what a technical sound method could look like. But before that, we also need to discuss certain sampling techniques, etc. So let us move forward. Here are some of the statistical terms that we typically use in econometrics, and that is random sampling. So the sample that we select should be drawn at random from a population. In the previous example here that we studied, the sample was not drawn at random, rather than all the European countries, they were selected. And European countries do not represent the entire world. If our data consisted of African countries, Asian countries, plus European countries, plus American countries, then we could have said that this is drawn at random and the sample represents all the population. And again, choosing a data at random means that each and every individual has equal chance of selection. If that selection is not equal, again that sampling cannot be random. A random variable is, on the other hand, a data of variable which is selected randomly. A variable that has the data which is selected randomly. That is a random variable. At econometrics, we usually use random variables. Then there is another way of sampling, that is independent sampling. Independent samples are samples that are selected randomly so that its observation do not depend on the value of other observations. For example, we have a deck of cards, and there are 13 cards of spades, 13 cards of hearts, and whatever. There are 13 cards of each of the set, you know that. And if we select one card randomly, we know that its chance of selection is 1 over 13. The probability of selecting a card of spades is 1 by 13, and we have excluded all other cards. Now once this card is selected, we replace it again. We put that card back, then again all the cards have the same chance, that is probability is equal to 1 over 13. But if we do not replace that card again, we do not put that card back into the deck, and we keep that card on the side, that card is removed from the sample, then the selection of the remaining cards is, the probability of the remaining cards is 1 over 12. So now since one card is chosen, the probability of other cards to be chosen has changed. This sampling is not independent, right? And independent sampling means that the selection of one card, the selection of one observation does not changes the chances of selection of another observation, right? In this case, for example, we have the data of life expectancy. The death of a person does not imply the death of a second person. So it means if one person die, it is not going to affect the life of another person. Another person should not die because of that person. This is independent. These two observations are independent of each other. Then another concept that is related to it is identical distribution. Means that when we have taken out a sample randomly, replaced it again, then we have another sample from the same population, both of them should have identical distribution. And we know the distribution, I have discussed the distribution, that most of the value tends towards its mean and lesser the values will be at its extreme. And if we have taken two samples, both samples have the same distribution. This means identical distribution. So when sampling has been taken randomly and that sample has independent observations and the distribution is identical, then we say it is independent and identical distribution, and we usually denote it as IID. So whenever you see IID with any type of distribution, it means independent and identically distributed. Now these concepts are related to our final question, the question number 4, which tells us that whether these methods are scientifically suitable, can we rely on these measures? So a good measure that we have taken has these properties. A good estimator must have 3 properties, and these are that the estimator should be unbiased. Means that the difference between the estimated value and the value from the population must be 0. If an estimator consistently gives us a value that is away from the actual value, from the population value, then that estimator has a biasness, right? So we cannot use that estimate. Arithmetic mean, on the other hand, does not have this biasness, so it is an unbiased measure. Then we have the second property of consistency. What is a consistent estimate? As the sample size increases, the estimated value converges towards its true value. So when we increase the number of observations in the sample, then we also approach to the true value of that estimator. For example, if we have taken arithmetic mean and we got a value of 15, whereas the arithmetic mean of the population is 18. So when we take more and more observations, our result may move towards 18 rather than moving towards the next average is 14, the other average is 27, and it is diverging. If it is diverging, it is not consistent. If it is converging, if true value is has been achieved by increasing the sample size, then this estimator is called consistent. Then finally, the estimator should be efficient. An efficient estimator is whose variance over multiple sample is lesser than competitive estimators. We have, for example, 3 measures, and for example, we have arithmetic mean, the median, mode. Arithmetic means considers the entire data, whereas median only takes the middle value. Mode only takes the value that is frequently repeated. Which one of the 3 measures is going to be efficient? It is obviously the arithmetic mean is more efficient, because the variance, if you take various samples, the variance of the mean, that is the mean that we are getting with each and every sample, that is almost the same. Whereas in median, sometimes we can get higher median value, sometimes we may get lower median value. So that is not such a reliable measure as compared to the arithmetic mean. And similarly, mode only tells us the value with higher frequency, and with various sample we may get various values that are repeated over and over again, and may have a higher variance. So efficiency, if these 3 properties are met in a statistic, in an estimator, that estimator is a good estimator. These 3 properties are, I repeat, unbiasedness, consistency, and efficiency.